Hello everyone, my name is Pejman and welcome back to the course of Deep Learning with the TensorFlow and Keras. As you remember, on last videos, we talked about a model for the deep learning. We started from a simple model, such as softmax model, that we have just one layer of softmax. And then we increased the capacity of the network, and we improved our performance on the classification. And at the end, we saw that, okay, we have still some overfitting. And we're back to this question that what we can do to solve this problem. So is our network bad design, or do we use too many of neurons, or data are not enough? So based on this question, we can say, okay, as we are using the MNIST database, and it's around a good database, I can say, from the size point of view. So we don't have this problem. So it can be too many neurons, or it can be bad network. So if we think that, okay, at the fully connected model, fully connected layers model, we stretch, or we make it our image flat. So it means that we lose all information on our image. So when we make it flat, we don't see any blobs, or we don't see any age on our image. So it's just an array. So if we wanted to get benefit of these features on our image, we cannot use fully connected models. So this is the point that we can think that, okay, this is the bad network for classification of images. So maybe if you are working with signals, it can be a good model that you have one array of signal. But when you are working on the image, so it's a little different. So for this, we can offer convolutional neural network. We saw a picture of the whole convolutional neural network, but here we describe how it's work. So in the convolution layer, we work on the spatial domain, or the spatial structure, I can say. So assume that we have an image like this, 32 by 32 by 3, so, and the depth is 3. It means that it's, for example, a RGB image, that we have the 3 channel of R, G, and B, red, green, and blue. So, and then we wanted to do convolution. So we should use a filter, and then we should apply this filter on image. So for ones that are less familiar with the convolution and how the convolution works, I can say that we apply a filter. So the filter, it can be at any size, 5 by 5, 3 by 3, or I can say 7 by 7. It can be like this, but usually I don't recommend you to use a bigger size of filter, as the cost of our algorithms will go high, because we have to do convolution. So we applied it on an image. So if I back, for example, we have the image of 32 by 32 by the 3, the RGB, and we have the filter size of the 5 by 5 by 3. So the same depth size. So it means that if you are working on the grayscale image, you don't need to have a filter size of, for example, 5 by 5 by 3. You just need to have a filter size of 5 by 5 by 1, because you're on the grayscale and you have just one channel. So we apply this filter on an image, and we do the convolution. We usually start it from top left, and we'll go slide it over the image to do the convolution. So I just briefly describe it. If you want to know more details how the convolution will do, you can search it on Google, and you will see lots of sources to describe this. So when we do this, we can generate one activation map. So when we applied it once on a specific location on image, we generate one value from that, and then we shift it by one pixel, and then the second value, third value, fourth value, and so on till end of our image. So here, after applying this filter on image, you can see we have such a convolvement, or we can call it activation map after convolution. So if we do this for the second time with another filter, we can generate one more activation map, or the convolution image. So convolved image. So if we do this several times, for each time we generate one activation map. So for example, here, as you can see, we have an image 32 by 32. We used 6 filters to generate the 6 activation maps, or convolved image that you can see here. So, and then we use it as an input of the next layer. So here you can see, and then at the end we can stack all these 6 images to have an image size of, it can be 28 by 28 by 6, or it can be at the same size of the input image, 32 by 32 size. And then for the next layer, this will be the input. So we know that if we wanted to use the new filter for apply on the blue images, or the blue this activation, we call it activation maps. The blue activation maps, we need a filter size of, for example, 5 by 5 by 6. So and we can do several times of this convolution. For example, here we show that we did it 10 times. Okay. So 6 times at the first convolutional conv layer, and the second 10 times for the second convolve layer. And we can do this several times and go on, and so on. So, and now that we understand how the convolutional layers work, we wanted to write a script to implement a model of convolutional layers. So here you can see we have an image of 28 by 28 by 1. So depth is 1. And then we define 3 conv layer, or convolutional layer. The first layer, second, and the third that we use. And usually in the convolutional layers, after each layer, we do the max pooling. The max pooling is just subsampling of image to usually to 2 times smaller than the previous one. For example, when we have 28 by 28, the second after applying the max pooling, it will be 14 by 14, and again after that it will be 7 by 7. We do this till the time that we have a small size of image. So for example, here, after 2 layers, we don't need to continue. And then at this level that we have features just on image, so it's not like for example a human on that image. It's full of features, any features, blobs, edge, or any type of features are in this. And then at this point, we can stretch it or make it flat and feed it to the fully connected layers. So by this, we go further and do the classification like our previous example. So if I wanted to show you how we can write a code for that, okay. So similar to the previous examples, we load the database here, MNIST database, and then we import models. So if you remember, we import the sequential, and then we import the dense function. So here, function dense and activation, of course. And now that we wanted to use also convolutional layers, so we have to add conv2D, because we are working on the 2D images. So 2D signals, I can say that it's image. So we need the max pooling to subsample or downsample the image. And then we use the flatten to make the image flat. So same as before dropout, we will use dropout, and this is for one-hot encoding, converting. So we use the, let me to run one by one, and we go further. So like the previous one, we use the tensor board to see the curves of loss and accuracy. We change the name to CNN softmax model. And then the same, we use the reshape function, but not for make the images flat. As you see, we make images as the size of 28 by 28 by 1. So 28 pixel, 28 pixel, and the depth that is equal to 1. And also we do it for the testing. And then we, similar to the previous one, we do the normalization to make it between 0 and 1. And then convert it to the one-hot encoding, the same as before. These are not new blocks. So here in our model, instead of using dense to make fully connected layers, we use conv2D, okay? And what we will write here, when we use the function of conv2D, convolutional in 2D, we should write the number of times that we wanted to apply this filter on image. So as you remember, we said that we slide one filter on an image, so it generates an activation map. And if we do this for the second time, it generates a new activation map. So we have 2. So it is the time that we wanted to apply this. So we can say that 4. So after first fully connected layer, we have activation map of 28 by 28 by 4. The depth is 4 because we did it 4 times. So activation, we use the ReLU as before. And the input shape is 28 by 20. We keep the shape of image. So, and then we do the max pooling. Usually, max pooling is used by the factor of 2. So we do the downsampling by the factor of 2. It's the common way. And as it is the max pooling, in a box of 4 pixels, it will take the maximum value of them and will replace it with on the new pixel. So we do this. We use the second convolutional layer, and we use 8 filters here, the same size of filter, and the activation map. Again, for the max pooling, we do the max pooling of 2, and for the last one, we use 12 filters, so by the same size and the same activation map. As you remember, I said that for the fully connected layers, we make a model like this from a layer with a high number of neurons, and then a little less, and less. So we can come like this, but for the convolutional layers, we should go like this. So in the opposite direction, we use a small number of filters at the beginning that will be on our image. So as we go further, our feature will be more complex. So we need more filter to extract better features for our model. So at the beginning, we use less number of filters. Then we go, it will be a little more, and then it can be as much as we want, but a little more than the previous layer. So, and then we make the image flat and feed it to the fully connected layers. We can consider 200 neurons here with the activation and the dropout of 0.2. And at the end, the last layer will be the same 10 neurons of that is the OR classes. So if we run it, we made our model, and then we compile the model. And at the end, similar to the previous one, we fit it let me to change it to 5, and then we'll run it. So it take more times compared with the previous one, but at the end it will generate a better performance for us. So if we go to the TensorBoard to visually see the results, so we can see here that it reached the accuracy of the validation. It reached almost to the 98.9. Yeah, you can see here at the black one. You can see 98.9 or 0.989. So it's a good improvement compared with the previous one that was around 97.9 or 98 maximum. So we had an improvement here, and for the loss function also we see that it came to the range of, for example, 0.04 or 0.05, something like this. And we did it. So we reduced the overfitting, we increased the accuracy, and it is the purpose that we have. So the best accuracy, the minimum loss. So if we wanted to compare all models that we developed or we implemented together, we can see here. This is the fully connected layer with the softmax. This is the fully connected layer with the ReLU. This is the fully connected layer with ReLU and the dropout. This is the CNN model, and this is the softmax, the simplest model. So come on. Okay, it takes time to load them, but even here, it's not loaded fully yet, but even here you can see that the loss function of the CNN model is much less than other models that we implemented before. And if we go for the accuracy, I don't know why it's like this. Let me to open it again. So here, if we write, let me to close the terminal of that. Let me to run it again. CMD TensorBoard log dir equal to logs alt slash. Okay, if it let's to copy. Okay, address. Okay, that should be okay. It works. Thanks. So if we have a look at this, you can see for the CNN model, we have as I said, we have the minimum loss and the best accuracy here. Also, you can see here the accuracy of all of your model, and you can see that CNN is the best one here, 98%, 92. So these models are, I can say that the simplest model that we can use for the classification. So you should customize these models based on your purpose and your data. So if you have a data in it's a bigger size, for example, instead of 28 or 32 by 32 or 28 by 28, if you have an image of 256, you should increase the number of layers, and it's based on the complexity of your image. You should increase the number of filters in each layer for the convolutional layer model or structure. So you can modify this or customize this based on your purpose and your data. So it's enough for this topic. And for the next video, I will show you how you can use your data or how you can call your data, because here we use an available library that load our data for us, the MNIST. But we should read our data and feed our data, our own data, to the network. In the next video, I will show you how we can do this. Thank you for watching. See you on next video.